Leonardo Pisano, better known by his nickname Fibonacci, which translates to mean son of a simpleton, was born in Italy in 1170. He was raised and educated in northern Africa, where his father Guillermo had held a diplomatic post. His father worked as a representative for the merchants of Pisa who were trading in Bugia. Because of this, he frequently traveled and brought his family, including his son Leonardo, along with him. It was here, in Bugia, that Fibonacci was first taught mathematics. He took advantage of the complex mathematical principles and understandings in the various countries that they traveled to, thus building the foundation for his lifelong passion for and career in mathematics. A little-known fact about Fibonacci is that for a while he went by Bagolo, which translates into traveler, an indication of just how significant his travels were to his life. Through his Mediterranean travels, he became exposed to the Hindu-Arabic numeral system and realized that it was much more efficient for calculation purposes than the Roman numeral system, which was previously being used. In the year 1200, when Fibonacci was only 30, he ended his travels and returned to Pisa, where he wrote numerous books on mathematical principles and developed his own novel concepts. He almost immediately wrote his first and most popular novel, Liber Abaci, and popularized the Hindu-Arabic numeral system in Europe. It was in Liber Abaci that Fibonacci introduced what was most likely his most famous contribution, the Fibonacci sequence, although it was later found out that the sequence had been detailed in early Indian mathematics.
Fibonacci's book, Liber Abaci, is one of his most well-known mathematic contributions. The book was published in 1202 after Fibonacci's return to Italy. It is based on arithmetic and algebra that Fibonacci had learned during his travels outside of Europe. The math of Liber Abaci touches upon the knowledge of previous discoveries, including those of Pythagoras, Euclid, and Diophantus, along with algorithmic methods derived from Arab sources. It has been adopted all over the world today. There were 3 sections of this book. First, Fibonacci explains the virtues of the Hindu-Arabic number system, which introduced the numbers 0 through 9 to Europe. It replaced the Roman numeral system. Fibonacci introduced Europe to the Arabic word zefiro, which became zeffiro in Italian and in the Venetian dialect zero, the name by which we know it in English and several other European languages today. It is presented as a placeholder and was new to Europe since the Roman numeral system did not have a symbol for zero. Fibonacci explains how to apply the new number system to the 4 operations addition, subtraction, multiplication, and division, always stressing the importance of practice in calculating these numbers. Fibonacci created a flexible, compact notation for handling manipulations with fractions. Fibonacci revealed a predilection for an Egyptian method of expressing a fraction as the sum of fractions with unit numerators using a tiny open circle placed in front or behind a sequence. The second section of Liber Abaci contains an extensive collection of problems aimed at merchants. It relates the prices of goods, how to calculate profit and convert currencies, and problems originated in China. Applications of his math extended into weights and measures, barter systems, business accounting, company profits, and much more. An example of one of the problems in his book is, if you will have 2 measure moneys, of which one is with 7 ounces and the other with 6 ounces, from which you wish to make 1 pound of money in which there are 4 ounces of silver, then you will wish to know how many ounces of each money and how much copper are to be adjoined. In the third section of the Liber Abaci, a problem led to the introduction of Fibonacci numbers and the Fibonacci sequence, for which Fibonacci is best remembered today. This problem is known as the bunny problem.
In the Liber Abaci, Fibonacci introduced a situation of population growth based on idealized assumptions, which he modeled using the scenario of a reproducing rabbit population. Fibonacci considers the growth of an idealized or biologically unrealistic rabbit population, assuming that first, a newly born pair of rabbits, one male and one female, are put in a field. Second, that the rabbits are able to mate at the age of 1 month, so that at the end of its second month, a female can produce another pair of rabbits. And lastly, that the rabbits never die, and that a mating pair always produces one new pair, a male and a female, every month from the second month on. The question that Fibonacci posed was, how many pairs will there be in 1 year? At the end of the first month, the rabbits will mate, but there is still only one pair. At the end of the second month, the female produces a new pair, so now there are 2 pairs of rabbits in the field. At the end of the third month, the original female produces a second pair, making 3 pairs in all in the field. At the end of the fourth month, the original female has produced yet another pair, and the female born 2 months ago produces her first pair, making 5 pairs in total. Thus, at the end of the nth month, the number of pairs of rabbits is equal to the number of new pairs, which is the number of pairs in month n minus 2, plus the number of pairs alive in the last month, n minus 1. This is referred to as the nth Fibonacci number. In his solution, Fibonacci developed a mathematical sequence which later became known as the Fibonacci numbers. Fibonacci began his sequence with the number 1 and calculated the next number in the series by taking the sum of the 2 numbers before it. Thus, a typical Fibonacci sequence reads 1, 1, 2, which is the sum of 1 and 1, 3, which is the sum of 1 and 2, 5, which is the sum of 2 and 3, 8, which is the sum of 3 and 5, 13, which is the sum of 5 and 8, 21, which is the sum of 8 and 13, 34, which is the sum of 13 and 21, and so on. The sequence rule, which was known to Indian mathematicians in as early as the 6th century, but brought to the West by Fibonacci in the Liber Abaci, reads x sub n equals x sub n minus 1 plus x sub n minus 2. Interestingly, every third number of the sequence is a multiple of 2, every fourth number is a multiple of 3, and every fifth number is a multiple of 4. The sequence can also be extended to the negative direction to yield a sequence of nega-Fibonacci numbers, reading negative 21, 13, negative 8, 5, negative 3, 2, and negative 1. Fibonacci numbers are also known to occur in sums of shallow diagonals in Pascal's triangle. Fibonacci numbers are intimately linked to what is called the golden ratio. 2 quantities are said to be in the golden ratio if their ratio is the same as the ratio of their sum to the larger of the 2 quantities. Expressed algebraically, the ratio reads phi equals a plus b over a is equal to a over b, where a is greater than b and b is greater than 0, and the Greek letter phi represents the golden ratio. Phi also equals 1 plus radical 5 divided by 2, or 1.61803398887. The closest rational approximations to the golden ratio are 2 over 1, 3 over 2, 5 over 3, and 8 over 5, all of which are consecutive numbers within the Fibonacci sequence. Thus, the sum of 2 consecutive numbers in the Fibonacci sequence is most likely to achieve the golden ratio when divided by the larger of the 2 numbers. Other names for the golden ratio include the golden mean, the medial section, and the divine proportion.
The implications of the golden ratio are widespread, as the ratio has extensive applications pertaining to architecture, music, nature, and even to the human perception of beauty. The rectangles circumscribing the Parthenon, the dimensions of the Great Mosque of Kairouan, and the measurements of the pyramids of Giza are all known to follow the golden ratio. It is found in artistic works, ranging from Salvador Dali's The Sacrament of the Last Supper to Leonardo da Vinci's The Vitruvian Man. In music, the ratio is critical for scales, which have 8 notes, chords, which are based on 3rd and 5th notes, musical frequencies, and even in instrument design. The golden ratio is also prevalent in nature and can typically be observed in the number of petals in a flower, spiraling patterns of pine cones, seed heads, shells, galaxies, and hurricanes, measurements of DNA lengths, and body proportions of various animals. In humans, the mouth and nose are both positioned at golden lengths between the eyes and chin, and the eyes measure between the ears at an average typically very close to phi. While all people are different, typically individuals with proportions adhering closely to phi are typically perceived as the most beautiful by the human eye. For example, celebrities known for their good looks, including Beyoncé, Tom Cruise, and Angelina Jolie, all have features which adhere very closely to the ratio. Fibonacci later wrote his second book, Practica Geometriae, in the year 1221. The book outlined and expanded upon the works of early Greek mathematicians Euclid and Archimedes. This book contains a large collection of geometry problems arranged into 8 chapters with theorems based on Euclid's book, Elements, and on divisions. In addition to geometrical theorems with precise proofs, the book includes practical information for surveyors, including a chapter on how to calculate the height of tall objects using similar triangles. The final chapter presents the calculation of the sides of the pentagon and the decagon from the diameter of circumscribed and inscribed circles.
The third book that Fibonacci wrote is known as the Liber Quadratorum. The Liber Quadratorum was published in 1225, and it translates to the Book of Squares. It is a book based on algebra, focusing mainly on Fibonacci solving different Diophantine problems. Diophantine problems are named after Diophantus, a 4th century AD Greek scholar who lived in Alexandria. These problems contain second-degree equations with 2 or more unknowns, and the solutions are required to be given as integers or rational numbers. This book was not as immediately influential in the world of mathematics as the Liber Abaci. However, it ended up being more original and an even greater masterpiece. The Liber Quadratorum is a systematically arranged, well-conceived collection of theorems. Most of these theorems were written by Fibonacci, however, others were discovered from Indian and Arabic sources. The book discovers numerous math problems and uses different proofs to explain the answers that Fibonacci finds. The concluding problem in the Liber Quadratorum is to solve the equation x plus y plus z plus x squared equals u squared, and end with rational numbers. The concluding statement that Fibonacci makes at the end of the Liber Quadratorum is, and not only can 3 numbers be found in many ways by this method, but also 4 can be found by means of 4 square numbers, 2 of which in order, or 3, or all 4 added together make a square number. Fibonacci is also responsible for the introduction of the square root notation into our system of mathematics. Fibonacci is famous for his introduction of the fraction bar. Beforehand, fractions were expressed using parentheses, and fraction bars made it much easier to see what was being performed during an algebraic problem.